Thank you for taking the time to watch this video. I'm Ryan Fitzpatrick, and the focus of this presentation is on a passage structure for plains fishes that was specifically designed to be replicated on other barriers in the study system and hopefully in other systems as well. But before I get to those details, I'd like to acknowledge my co-authors, first being David Longrie. David is a project manager supervisor for Colorado Springs Utilities, and he came up with this design that I'm going to discuss today. It should be noted that David won the Colorado-Wyoming Chapter Max Award of Merit for his efforts on the structure. The other two co-authors are Ryan Freebertshauser and Paul Fouts with Colorado Parks and Wildlife. And I'd like to begin this presentation with this classic figure from Schlosser and Angermeyer about habitat needs for stream fishes to complete their life cycle. They need spawning habitat, mosaic of feeding habitats, and refuge from harsh environmental conditions. And they need to be able to access all of these different habitat types. Now, plains fish, even though they're small-bodied, many species require much larger spatial scales to complete their life cycle than you would think. So these arrows are much longer than one may assume for a small-bodied fish. Unfortunately, they're not very good at jumping over barriers. So in these long arrows between these habitat types, even a small blip, a small barrier in here could disrupt the life cycle. And this is important because, as you can see on this map that was graciously provided by Eric Richer, unfortunately, there are a lot of barriers on the landscape. Providing connectivity is an important conservation issue, not just for plains fishes, but for stream fishes throughout the state. And that brings us to our study area, which is Fountain Creek. Fountain Creek is located in south central Colorado. It flows to the south through Colorado Springs to its confluence with the main stem Arkansas River and Pueblo. The diversion structure that's going to be the focus of this presentation is Owens Hall diversion. And as you can see, that is the first barrier of fish moving upstream from the confluence with the main stem Arkansas. That's the first barrier a fish will encounter. So as I mentioned, a main motivating factor for this project was to provide a template that could be used for passage and deployed on other barriers moving upstream, because there are several barriers between Owens and Colorado Springs. They're just not depicted on this particular map. Now, Fountain Creek has a native species dominated assemblage, including the state threatened Arkansas darter, as well as the species of concern flathead chub. We want to do everything we can to conserve that assemblage. Fountain Creek is a plain stream, which of course lots of sand, but the sediment load in Fountain Creek is extremely high. So not only would a fish passage structure need to pass fish, but it needs to transport sediment effectively as well. The other unique factor with Fountain Creek is the flow regime. It's very flashy. This is a flow regime on Fountain Creek at Pueblo from 2015 to present. And as you can see, these base flows generally are around 100, sometimes lower, sometimes higher, depending on the year. But what really stands out are these high spikes in flow, up to 10,000 and in this case, almost 20,000 CFS. But you can see these fairly repetitive high flow events, mostly due to monsoonal thunderstorms, that increase the flow from 100 to several thousand CFS. So the fish passage structure has to pass fish, it has to transport sediment, and it has to handle these very harsh conditions in Fountain Creek. If you bear with me for a moment, I have a few videos that I'm going to incorporate, and they show up much better if I take off the thumb image. There we go. So this is a video taken on the Owens fish passage structure, on the Owens diversion structure before the fish passage structure was put in place. And if you look down in this area, you will be able to see flathead chub trying to swim up the barrier. There they are. And this is what really instigated this project. Gary Dowler, a retired Colorado Division of Wildlife aquatic biologist, he saw this and reached out to Colorado Springs Utilities about opportunities to install a fish passage structure to increase connectivity in the system. And as the camera pans to the left, you'll see how large the structure is and how those fish weren't really even getting close to the top. This barrier is approximately 2 meters high. So that was the first engineering difficulty that David had to solve, was getting this large of a barrier, a passage structure on it, but the passage structure had to fit on, go a little bit further, it's not quite clear, this apron. There's a concrete apron at the bottom of the structure here. So it had to fit on this apron, get over a 2 meter high barrier, but still have a slope low enough for fish to be able to ascend the structure. And this is what he came up with. That video you were just watching, I was standing, there's a platform on the sluice gate. The camera was just held down and shooting this way. So David developed this serpentine design that has 4 main components. The first are these straight sections right here, these curved sections, these pillars, and then depending on the barrier the structure is installed on, there might need to be a specialized either exit, which we had here, or an entrance, which we did not use. We just had fish enter into a straight section of the passage structure. Now, these straight sections are what make this design adaptable to different barrier sizes. Depending on how high the barrier is, you can add or subtract the number of straight sections and corner sections to get over that particular barrier. You can also adjust the size of these straight sections. For us, we had 2 straight sections. They were each 14 feet 9 inches. But if you had a tighter area that you needed to install the barrier on, these could be cut down as well. Regarding costs for the structure, these are all pre-pandemic costs. I'm sure these have increased, especially the concrete, due to supply chain issues. But the overall cost for the fish passage structure was $450,000. Now, a lot of that was research and development to come up with this precast design. If you were going to use this design, you would not, I don't think you would approach that dollar figure. In fact, you can get an idea of what the cost of this design would be on your barrier by taking the height of your barrier and determining how many straight sections at $9,000, curved at $6,000, and foundation sections at $4,000 to get over that height and get a rough estimate of what that fish passage structure would cost. Additional considerations, as I mentioned, you might need to make a passage entrance or exit if there's something unusual about the barrier you're providing passage over. We had a cap to limit sheet flow over the top of the structure. You need to divert and dewater the creek during construction. And depending on the barrier that you want to install this fish passage structure on, you might need additional foundation construction to support the precast sections. Because these are poured concrete, they are extremely heavy sections. So you want to make sure the barrier can support it. So here's the final product for scale. This is Carly Baum. Many of you know Carly. And to determine if fish were able to ascend this fish passage structure, we conducted a mark-recapture study. We deployed 12mm half duplex pit tags and fish from July through November 2020. And we also installed 3 arrays on the structure itself. Here's array 1, array 2 in the middle, and array 3 at the exit. And we put this array on this curve because the entrance is down here, but at different flows, this area can be inundated with water. And we wanted to make sure if we got a detection of a fish, be sure that that fish was in fact in the passage structure. Those arrays feed into the reader box and tuners that are attached to the sluice gate right here. As a quick tagging summary, we deployed a total of 1,327 tags in 8 species. Of those, we had 37 detections in the array. So not a lot of data here, but we were able to run Cormack-Jolly-Sieber model to analyze these data. Now with this model, it derives 6 parameters. The first is a survival parameter from release to array 1, which is phi1, array 1 to array 2, which is phi2, array 2 to array 3, which is phi3. It also estimates detection probability for each array, which are P1, P2, and P3 respectively. Covariates included array and fish total length as an individual covariate for both phi and P. We ran intercept models, individual models, and additive models, which resulted in a model set of 16 models, of which 8 had weight, and that's what's presented here. The top model was phi array and P total length. Now the beta for this total length was positive, indicating that larger fish had a higher detection probability than smaller fish. However, that confidence interval did slightly overlap 0, so that was a weak relationship. As you can see, many of these models have very close delta AIC values, and many of the models had weight. So we decided to model average the parameter estimates, which is what I'll walk through here. So first, phi1, which is release to array 1, was 0.03. So there was a 3% probability that fishes released just downstream of the array would get, just downstream of the passage structure, would get detected by array 1. And that's pretty low probability. We'll come back to that. But once they're in the structure, array 1 to array 2 had a phi of 0.89, and array 2 to array 3 had a phi of 0.99. So very high probability of successfully ascending the structure once they were in it, but we need to increase this phi1, this 3% probability, and I'll spend a slide later in the presentation to expand on that. For detection probability, we were nervous because the passage structure had a lot of rebar in it, and that metal can interfere with these arrays' read range. However, the P's came out very high, P1 0.98, P2 0.97, and P3 0.98. And this is due to, we didn't need a very large read range. You know, it was only like 6 inches or so from the top of the structure to the bottom, maybe a little bit more than that. But luckily we didn't need a large read range, and the arrays did well. For the construction of the arrays, we used 4 loops of 12 gauge THHN wire, and obviously it seemed to work. That design worked well. Timing of movements. This was interesting because Tyler Swar and Colbertan conducted laboratory experiments, and one of the species they used in their experiments were flathead chub from Fountain Creek. And they both noted a pattern of increased movement at night, which was a little bit surprising. And we wondered if this was an artifact of that being laboratory experiments. And Fountain Creek is a very turbid system. When they were in the lab, that water was much clearer, artificial lighting. So we wondered, is this really a pattern that you would see on the landscape? This figure has time of day on the x-axis, and you will see a few times that have asterisks because, as I said, this study went from July through November. So depending on what day the detection occurred, we had to look back and see if that detection was in fact during the day or at night. On the y-axis, you see the frequency of pit tag detections. And obviously, this pattern of more movement at night was corroborated with field data, which is great. And it wasn't just flathead chub. White sucker also had this pattern of increased movement during the night. And this has implications for urban fish passage structures. If there's artificial light that are bright lights near the passage structure, there may not be, that may reduce the probability of fish using that structure. Maintenance. As I mentioned, sediment was a large concern. We were concerned that during high flows, sediment would get on the structure, then when those flows drop, it would just fill up with sediment. However, as you can see here, very clear That sediment's getting cleared off very nicely. We haven't really had any sediment issues in the structure itself. David deserves a lot of credit for developing this design to pass as much sediment as there is in the system. One thing we could not control, however, was large wood coming down Fountain Creek and getting impinged on the structure itself. Now, there really wasn't much we could do. We could have gone out with chainsaws and try to chop off a lot of this large wood, chop it into pieces and get it off the structure. But with the flow regime in Fountain Creek, most of the time we just decided to let it be, wait for the next high flow event to wash it off the structure. However, there was a little bit of a Goldilocks zone here. Smaller pieces of debris on the structure actually produced what looked like nice fish habitat in the structure itself. Now, getting to attraction flows, this deals with that phi1 of 0.03. So again, 3% probability of fish being released downstream here, ascending the structure and being detected by this first array here. Now we do have fish stacked up here. They can get over this barrier at higher flows, and they stack up here, and they stack up here. As I go through this video, you can see those are nice looking flows. You can see why fish are attracted to it. And even when the sluice gate is closed, there is some flow that comes through that could attract fish. So the big problem here is, what can we do to keep fish not being attracted to that area, and over here, and push them into our fish passage structure? It's almost, unattraction flows or negative flows in other areas, so that they actually select the opening here and get into the passage structure. So if anybody has ideas for attraction flows, I'm all ears. I find that really interesting. It's kind of the next phase of this project. That's the last video, so I'm going to stop share here real quick. Okay. So the conclusions are, first and foremost, it worked, and it worked in three, the design worked in three important criteria. Number one, it's still standing. You saw the flow regime in Fountain Creek. That's a very harsh environment for a passage structure to sustain, and it's still standing and functioning today. Two, it passed sediment. It was able to transport sediment through the structure, which was very important in the system. And three, it had a high fish passage success rate once fish were in the structure itself. Again, these attraction flows are important. What can we do to get more fish in the structure itself and get them over that barrier? Fish move through the passage structure fairly quickly. The median time for successful ascent was 19 minutes, and the minimum time was 6 minutes, which is pretty impressive considering, again, fish have to swim through 123 meters to fully ascend this fish passage structure. And again, most movement occurred at night, which corroborated the laboratory results seen by Tyler and Cole. These are the references if anyone is interested. And with that, a lot of people to acknowledge, first and foremost, Colorado Springs Utilities for funding this project. They deserve a lot of credit because passage structures a lot of times deal with mitigation, and there was no mitigation involved in this. They were made aware of this conservation issue, this connectivity issue, and they really came to bat with money, time, and this design. So greatly appreciate Colorado Springs Utilities, other folks at Colorado Springs Utilities, as well as Colorado Parks and Wildlife, and other agencies that were involved in the initial discussions for this project. And with that, if you have any questions, if you would like the technical plans, or again, if you have any ideas for the attraction flow, I'm all ears. Please send me an email. And with that, thank you for watching the video. I look forward to seeing everyone in person next year in Fort Collins. Thank you.